Hi everyone. Today we are going to learn divergence in curl. Okay, so new terminology today. We learned divergence in Calculus 2, right? Yeah. So we have a divergence here. So let me just read the vocabulary, the definition of divergence. So how the vector field behave toward or away from a point. Okay, that means flowing out, flowing in, right? But then we learned those kind of terminology earlier, right? Right, flux, right? Very good, good point. So we learned flux earlier section. They talk about the flowing in, flowing out, right? Okay, then what's the difference with divergence with the flux? So divergence is for a point, we just talk, right? Behave toward or away from a point, right? Then flux, same as flowing in, flowing out across the surface or curve. Make sense? Okay. Now, we will learn about the curl later. So what is the curl? It measures how much the vector field is rotating around the point, right? Okay, then this is a very similar earlier what we learned about circulation. Yeah, they talk about the rotating too, right? Okay, then curl is about the local and circulation is about the global. So what this mean? So curl is a local. That means how much is the vector field spinning right here? Circulation is global. What does that mean? How much total spin is there around entire boundary? Make sense? Okay. So let's do divergence first. So we have the formula divergence. We have vector field, the equation or function PQR. Okay, now we are using divergence, just the first three letters, divergence, div, and then using vector field f. Then we want to find the partial derivative with respect to x, and we want to find the partial derivative with respect to y, and we want to find the partial derivative with respect to z, respectively from P, Q, R, right? We add everything, then we can get the divergence of vector field F, yeah? So we add everything, right? And then we say the point, there will be a number, right? Okay, so look, divergence, we are going to think about in the like flowing out point of view. Means that we might think outflowingness. Okay, so what this means? Let me talk about outflowing first. So divergence is positive. That means there is more flowing out than in. I told you divergence, we think about from point of view from the outgoing, right? Outgoing, outflowingness. So if there is more out, then we say that divergence is positive. If there is less flowing out, then divergence is negative. It's flowing out is the same as in, this is 0. Make sense? Okay, so we think about outflowings first. So flowing out more than positive, less negative, same as in 0. Okay, let's do the example. So we have vector field, negative y and x. Then the first one, p, and the second one as q, as the equation. All right, now the formula we have divergence of vector field f. Then we are using, since we have 2 dimensions, we can use that partial derivative with respect to x plus partial derivative with respect to y, respectively, from p and q, right? Okay, now what is that? What is what is that? You don't know anything. What is that? Yeah. So what is partial derivative with respect to x? So that is, we're looking at p, right? What do you get, this one? So there is no x. So it's 0, right? So we get 0. And look, we're looking at q. And we want to partial derivative with respect to y. Okay. There is no y, so it's also 0, right? So we have 0 plus 0, which is 0. So means that 0 divergence. Okay, what this mean? This means there is the same amount flow in and out, right? So flow in, same as flow out. Okay, so here is the picture, how it looks like. So 0 divergence. So this is the one. Zero divergence. Actually, this one, yeah, this one is that, right? This one, we did that. So this one, yeah, why I did not this one? Let's do this one too. Okay, this is the one. So this is the one, vector field. We have negative y and x, 0 divergence. This one looks like when you talk about the rotational vector field, right? So this is also, let me write down, rotational vector field. So we get in the case 0 divergence, right? Okay. Let's do this one. Number 1, 1, 2, right? So 1, 2. So vector field, we have 1 and 2. Okay, we want to find the divergence of vector field of F. Okay, then we do partial derivative with respect to X. What do you get? So this is P, this is Q. So we have a 0, right? And we're looking at the Q, partial derivative with respect to Y, constant. So it's also 0, which is 0, right? Okay, that will be the first one, this one. 0 divergence. That is the one. Okay. So same concept earlier means the same amount of flowing in and out, right? So 0 0 divergence, divergence. Okay, let's do number 3. Let me using this one. Okay, let me arrange number 1 and 2. Swap, right? Okay, so third example. So we have a vector field. We want to find divergence of that vector field. So divergence of vector field. So partial derivative with respect to x from the p equation or function, right? And we want to have partial derivative with respect to y from the q function or q equation. All right. All right. Now we want the derivative with respect to x. We have a negative x, so it's -1. And partial derivative with respect to y, we get -1 as well. And we get -2, right? Okay, good. So we have a -2 means from the divergence, right? So flowing out is less than flowing in, right? That's a negative divergence, right? Yeah. So that is less than 0 means negative divergence. Okay. So means that uh, less flowing out than in, right? In other words, there's more flowing in than out, right? There is more flowing in than out. All right. Okay, so this is the picture of the negative divergence. So we can see that everything is in, right? To the one point. Yeah. Okay. Oh, also this one from previously we learned this is radial vector field, right? So this is the one they're using. Oh, they already say that here, radial vector field. They already say that radial vector field. Oh, they're using R instead of F. Yeah. Okay, so we have a last example. So we have vector field, and then we want to find divergence of vector field. Okay. Divergence means the flowing in and out at the point, right? So we're gonna find actually the point, whether zero divergence or positive or negative, right? Okay, so that is, we have a PQ or PQ or or okay, so we want the partial derivative with respect to x, y, z, right? From the equation p, q, r. Okay, we added them. So we're looking at the p, partial derivative with respect to x. Then we get e to the x power, right? And we're looking at the q, partial derivative with respect to y, then z is constant, so we keep that constant z, right? Okay, now we're looking at the r, partial derivative with respect to z. Oh, then 2z, right? But then y is also constant, so 2 negative yz. Make sense? Okay, I don't have to write down, right? You know it, you know that, right? So negative 2yz. Okay, now we want to know about the divergence at the point, right? So we want to know about divergence at the point 0 to negative 1. So there will be x, y, z, right? So x, y, z. So there will be e to the 0 power plus negative 1 z minus 2 times 2y z, which is negative, right? Okay, so the e to the 0 power, which is 1, and then negative 1, that's 0, right? So this is 0, and we have positive 4. So positive 4, which is positive divergence, right? So greater than 0, positive divergence. So positive divergence means we think about the outflowingness, yeah? So we have more flowing out than in, right? Okay. More flowing out. Okay, let me show you how it looks like the divergence, this vector field, but I cannot get at the point, all right? All right, so I showed you from the textbook what is zero divergence looks like. So one has rotational, right? Yeah, one is rotational. One is like this, zero divergence. And then other one is negative, right? So negative, more in, and then positive, more out then, right? More out. Okay, so let's take a look here. This one from Calc3D, yeah? I was using in the select vector field, and then I typed, oh, it's gone, huh? Man, oh, right there. So normally they give us like that, this form. Yeah, I cannot make a, oh, I can, oh, I can annotate it. Oh, good. That's good. So normally they give us like that, right? Yeah. And then I should Okay, this is Z, Y. All right, now I typed it partial derivative with respect to X for the M here. And then I typed the partial derivative with respect to Y, second one, and then I'm looking at the bottom. Yeah, can you see that? And then I typed partial derivative with respect to Z for the P. Yeah, so click that. So that is the one. Yeah, we can see that every arrow is going up, right? So, but can you see that here? Here, can you see that? Yeah, there, okay? This is the number of vectors. X-axis 9 there, Y-axis 9 there, Z-axis 1 there, right? Yeah. What if I make, okay, let me click use a fixed length for all vectors. There one. Didn't work. Looks like Z. Yeah. Z. And confusing. X, Y. I want to make this way. Okay. Yeah. So what is called? Thumb? I forgot. So Z, X, Y, right? Yeah. Correct? All right. Okay. Oh, this, it worked earlier, but it's not. It's okay. Okay. Number of vectors, let me type along Z axis like a 9 as well. Here. Yeah, 9. Return. Oh, this is not done. Okay, what's going on? Maybe. Oh, this was unclick. I should have unclicked this one. Okay. Oh, I clicked that on this one. Oh, is it possible? Okay. So let me do that. Use the same vector length, and then 999. Yeah. Look. Can you see that? You think everything is going out? Yeah. Then what about in the bottom, right? Bottom, right side, bottom. Looks like going inside. Yeah. Okay. So little bit less then, little bit less, right? Okay. Let me screenshot and then organize in the note. Okay. But then let's see, at the point we wanted to know about divergence at the point 0 to -1, right? So 0 to -1. So we start to x equal to 0 and +2 for the y and -1. It's over here. Yeah. So that is 0 to -1. Yeah. Is it good? Okay, so we have another terminology about magnetic field. So magnetic field is also a vector field. And then we are using this dot product. So gradient with the dot product of the magnetic field equal to 0. That means divergence of magnetic field is 0, right? So that is, we can say that divergence magnetic divergence of magnetic equal to 0. Yeah. Okay, let's do this example. So is it possible for that vector field? It's a magnetic field. Okay, then we need to show that the divergence is equal to 0, right? Okay, let's show that. So since they're using F, we are using F, right? All right, so divergence of F equal to partial derivative with respect to X plus partial derivative with respect to Y. We add them to show that equal to 0. All right, so let's take a look. P, we want to derivative with respect to X, then we get 2X, yeah? But then Y is constant, so we have a 2XY. Okay, now we're looking at the Q partial derivative with respect to Y. Then we have a 2Y. Then X is constant, so we have a negative 2XY, right? Okay, so we have a negative 2XY. We get 0, yeah? Oh, it's not? Oh, I totally forgot we have Y there. Sorry about that, right? Okay. So second term, negative 2XY, that's correct. But what about the first term? So it's 1, right? So 1 minus that. So we insert 1. That's for the partial derivative with respect to Y for the Q equation, right? Or Q function. All right, then 2XY minus 2XY is 0. Then we have 1 there, right? So 1 is not equal to 0. Then the vector field is not the magnetic field, right? So okay. Okay, so we have a new terminology about source-free. So source-free field is a vector field that has stream function. So what kind of stream function? So we have a flux, flow in, flow out, right? So with the flux, that is 0 along any closed curve. Yeah. Okay. Then let's take a look. We have the vector field PQ is a source-free continuous vector field with differentiable component functions. Then the divergence of a vector field equal to 0. Yeah. So this theorem, same as earlier. Okay, now let's do this. Is a vector field, we have a 2-dimension, source-free, right? Then we have to show that the divergence of a vector field equal to 0. Yeah. So show divergence vector field equal to 0. All right, so divergence vector field. Let's looking at the P equation, P function. We want to partial derivative with respect to X. Ooh. Then we have a 2X. Y is constant, we keep the Y, right? And we're looking at the Q. Partial derivative with respect to y. First term is 0. Second term, 2y, negative. And then x is constant, we keep the constant. So negative 2xy, right? So negative 2xy, we get 0. Okay, then it's a source free, right? Thus, f is source free. Okay, you cannot see in the bottom, yeah? So thus, the vector field is a source free. Okay. All right, so basically we might think the source free as, oh, cannot, there's no next page. Hold on one second. So I said earlier, right? So source free, we might think zero divergence, right? Divergence, right? So what was zero divergence, right? So there is no flowing in, no flowing out, right? So we can think about that, right? So means zero divergence. So means that no flow in and out. All right. Okay. Finally, we're gonna do curl. So we introduce what curl was, right? In the beginning. Okay, let's do one more time. Curl measures the extent of rotation of the vector field about a point, because we talk about the rotation as a local, right? So at a point. And also it measures of a vector field's spin at the point, right? At the point, local, right? Okay, now we have a definition. Let's take a look. We have a cross product with a gradient with a vector field, right? So we have ijk cross product, which is determinant, right? All right, then we can have the formula. So ijk plus minus plus, right? Then we are using this one, and we multiply this way, then subtract another diagonal, right? So we have that. J, same concept, right? K, same concept, right? Okay. I have a note here. So curl is 0 if only if and only if we have a simply connected domain, a vector field is conservative. Okay. So curl is 0 if the field is conservative, then that conservative has must be simply, the domain is simply connected, right? Okay, then there is another note for this one. Conservative field always has 0 curl, okay? All right, now we have a vector field is constant. Then constant with head like this, right? So 1 and 2 constant vector field. Then there is no spin. That means curl is 0. Okay, there's another note. A 0 curl does not guarantee the field is constant. So we have a constant. There is 0 curl. We can say the curl. Then 0 curl does not say the vector field is constant. Yeah, not always. Yeah. Okay. The wheel rotates in the clockwise direction, so like that. Then it causing coefficient of curl to be negative. So negative coefficient basically, right? If we have positive coefficient, then that is counterclockwise. Yeah. Okay. Now let's do this one. Find the curl of the 3D of vector field. Okay. So I wrote down the formula here. Okay, let's do that. So we're looking at the R. Oh, we're looking at the R. And we do partial derivative with respect to Y. Yeah. Okay, we have to be careful. A lot of variables. So partial derivative with respect to Y means we treat xz as constant. So we have xz, right? So there is xz. And then we're looking at the Q, partial derivative with respect to Z. That means the first term is 0, second term is x. Plus, and we're looking at the P, partial derivative with respect to Z. So we get x squared because constant. And looking at the R, partial derivative with respect to x, then yz, because yz is constant, right? And j, we're looking at the q, partial derivative with respect to x. Okay, first term is 0, second term we have a z, right? And looking at p, partial derivative with respect to y, there is no y, so it's 0, so just k. Yeah, that's it. You guys okay? Okay, so we have two dimension of the vector field. We want to find the curl of the vector field. Okay, so I brought the formula from 3D of curl of a vector field. Okay, then this is a P and Q, right? We don't have a R because 2D, right? So R in the case we don't have, and then Z, we don't have the Z, right? Yeah. So we cross out this one. Once again, we don't have a Z because not 3D, right? And then we don't have R, so we don't have a second term. Okay, now we have Q and X, we have P and Y, right? So we keep that. All right, so that means we're looking at the Q partial derivative with respect to X, subtract, and we're looking at the P partial derivative with respect to Y, right? In K, right? So we have the formula in 2D. Curl of F equal to Q of X minus P of Y and vector K. Okay, why we have a K, huh? Something weird because we are talking about 2D, right? So this means how much the field is rotating in the plane, 2D plane, right? XY plane. And the axis of that rotating is the z-axis, which is perpendicular to the xy plane. So this result of a 2D dimension of curl is in the k direction. That's why. All right. And we started with the 3D earlier, right? And then we started from the cross product from the beginning of the definition of curl of a vector field F. Yeah. So I hope you understand why we have a k direction here, right? Okay. We have not finished this question, so let me finish that and we do one question and then we're done. All right. Okay. So we want to partial derivative with respect to q, respect to x, right? So it's a constant, so it's a 0. Then we're looking at partial derivative p, partial derivative with respect to y, which is 1. And then k direction, right? So we have to mention that. Okay, so there will be negative 1k. So we have negative means that they're causing the what is called clockwise direction, right? Yeah. So negative direction clockwise. All right. So here's the picture. So they say that wheel rotates in the clockwise direction, negative. Yeah. So negative clockwise direction, negative clockwise direction. So this is the picture. So clockwise. Okay, so last question here. Use the curl to determine whether this vector field is conservative, right, or not. Then we had the note, conservative field always has zero curl. So let's show that whether this is a zero curve, zero curve of vector field, yeah? Okay, so I brought the formula here. So let's do this. So we have to be careful, a lot of variables there. We're looking at the R, and then we want to derivative with respect to Y, then X is constant, so it's X, yeah? And looking at the Q, we do partial derivative with respect to Z, and X is constant, so we get X. And we're looking at the P, partial derivative with respect to Z. Y is constant, so it's a Y. And we're looking at the R, partial derivative with respect to X. That is a Y. Y is constant, right? And looking at the Q, partial derivative with respect to X, Z, because Z is constant. And we're looking at the P, partial derivative with respect to Y, then Z as well, because Z is constant. Okay, yeah? Okay, everything we get the 0, yeah? If we have curl of F equal to 0, then we can say that this is a conservative, right? The vector field F is conservative. Okay. Any question? All right. Thank you for watching. I will see you in the next video. Thank you. Bye.